Okay, prove that the sequence un with nth term un equals 2n minus 7 over 3n plus 2 is, well, first thing we need to prove is that it's monotone increasing. Monotone means over the whole of its domain it is increasing, and we then need to prove that it is bounded. So that means we can pick two definite values such that it doesn't go beyond these values. So one would be a lower bound, one would be an upper bound. It could potentially reach that value, but we need to guarantee that it doesn't go beyond it. And we've not been asked to actually show what the bounds are. We probably will end up doing that. But if you're just showing that it's bounded, it's not absolutely necessary to do so. So if we just look at the monotone increasing bit first, now there's more than one way to do this. The most common ways, you can think about the current term and the next term. So if something's monotone increasing, then the next term, so that will have un plus 1, will always be greater than the current term. Right? So that is one way to show it, and you can do that algebraically. A much more useful rearrangement would be to show that the next term, if you subtract the current term from it, then that will be greater than 0. So if we can do that, we show that the sequence is monotone increasing. Another thing you could do, you could write the sequence as a function, as in replace the n's with x's. So in this case, we might call it 2x minus 7 over 3x plus 2. And then you could show that, say, f of x, or f dashed x in, you could show that that is positive over the whole of the domain for a sequence, a natural domain, being all positive integers. So if you show that that is true, then that conclusively proves that the sequence is monotone increasing. You could, if you had something that looked geometric, e.g. if it looks like to get from the current term to the next term, you multiply it by something, by a common ratio. If you can show that that ratio is well, the absolute value is greater than 1, and then it would depend on the signs, the sign of the first term and the sign of the ratio. You might be able to use that to show that it's monotone increasing, but you definitely can't use it for this because it's not geometric. So for this, to be honest, using the derivative or using this un plus 1 minus un, I think probably the amount of work involved is similar, but I am going to use this first method. So we're going to get an expression for the next term minus the current term. So the next term, well, if the nth term is 2n minus 7 over 3n plus 2, then the n plus 1th term, we just replace n with n plus 1, make sure you use a bracket. So un plus 1 minus un, well, that is going to equal, it's 2n plus 1 minus 7 over 3 n plus 1 plus 2, so that's the n plus 1th term. We subtract the nth term, which is just given to us, minus 2n minus 7 over 3n plus 2. And something like that. I'm going to have to do quite a lot of tidying up for this. So the first thing we're going to look at is this, this first term, so let's get rid of those brackets. So 2n plus 1 minus 7 is going to be 2n plus 2 minus 7, which is 2n minus 5. 2n minus 5 in the denominator. 3 brackets n plus 1 is 3n plus 3, plus the 2 must be 3n plus 5. And then minus 2n minus 7 over 3n plus 2. So now if we look at that, remember all I'm looking to do is show that this is always positive for monotone increasing. So what I am going to do, I have one expression for this, and there's no friendly common denominator that jumps out at you, so sadly you're going to have to cross multiply to find the denominator. So it's going to be 3n plus 2, 2n minus 5, minus 3n plus 5, 2n minus 7 all over 3n plus 5 and 3n plus 2. So we are definitely going to expand the numerator. There's no advantage in expanding the denominator. Remember, all we need to do is show that this thing is always positive. So actually, if you think about the denominator, look at the denominator, there's enough there anyway. I'll discuss that in a bit more detail, but you can see on the bottom of this thing, there is enough information to say that the denominator will always be positive for positive integer n. Okay, so on the top, you're going to have 3n times 2, right? So 6n squared. 3n times minus 5 minus 15n. 2n times 2 is 4 plus 4n, so that's minus 11n. 2 times minus 5 is minus 10, minus, don't forget the bracket. 3n times 2n is 6n squared. And you've got 3n times minus 7 is minus 21n. 5 times 2n is plus 10n, so minus 21 plus 10 is minus 11n. And you've got 5 7s are 35, so that must be minus 35. So this is going to simplify it nicely over 3n plus 5, 3n plus 2. So looking at the top, because of this bracket, you've got 6n squared minus 6n squared, so that's just going to be nothing. The same case with the minus 11n, so minus 11n minus 11n will just get us to 0 as well. So you've got minus 10 minus 35, which is 25. So now this equals 25 over 3n plus 5 over 3n plus 2. Now remember, n is a positive integer. So 25 is obviously positive, so this is positive over, well, for positive integer n, well, 3n will be positive, 3n plus 5 will be positive. Very similar argument for the 3n plus 2, so you're going to have another positive times a positive on the bottom. So that means that un plus 1 minus un is always greater than 0 for positive integer n. And that means that un is monotone increasing. Well, it's monotonic and it's monotonic increasing. Remember, monotonic means it's either increasing or decreasing over the whole of its domain. And obviously then we just say, well, which one is it? So the second part of the question, we need to show that this is bounded. So we need to show that un equals 2n minus 7 over 3n plus 2 is bounded. So basically, because this part 2, as un is monotone increasing, so u1 must be the smallest term, right? u1 must be the lowest value, e.g. the lower bound. So it is 2 times 1 minus 7 over 3 times 1 plus 2. So u1 equals 2 times 1 minus 7 over 3 times 1 plus 2. So that is, well, 2 minus 7 is minus 5. 3 plus 2 is 5, so minus 5 over 5 equals minus 1. So lower bound is minus 1. Now for the upper bound, you've got options. There's kind of a quicker, or it could be argued that it's quicker and possibly easy, depending on what you're trying to find. you could get a bound that's not really anywhere near the actual upper bound, but it does show that it's bounded. So I'll show that first. So basically, un equals 2n minus 7 over 3n plus 2. So basically, we can very quickly show that this will never get beyond 1 if you think about it. So for the n's that we're interested in, which are positive integer n's, so for positive integer n's, 2n is always going to be less than 3n, and the minus 7 is going to be always less than 2. So the reason why we pick those is because you've got a 3n here and a 2 here. So if 2n is always less than 3n and the minus 7 is always less than 2, so 2n minus 7 over 3n plus 2 is always going to be less than 3n plus 2 over 3n plus 2, because obviously the smaller the value of the numerator will make the whole thing smaller. So 3n plus 2 over 3n minus 2. So 3n plus 2 over 3n plus 2 is obviously 1. So that means un is always going to be smaller than 1 for positive integer n. And hence, un, well, we know it's now smaller than 1, and we know it's greater than or equal to minus 1, and therefore un is bounded. Now, for that, I think that was possibly a strange-ish way of doing it. I don't know if you would actually do that under the pressure of an exam, if you had something this simple. Because yes, all the terms in the sequence are greater than 1, but in reality, they don't actually get very close to 1 at all. And if you just look at the thing, you could very quickly find the limit of that. So if we just looked at the limit of the sequence as n term approaches infinity, so the lim as n approaches infinity of 2n minus 7 over 3n plus 2, well, we know we just divide by the highest power of n, which is just n, equals the lim as n approaches infinity of 2n over n minus 7 over n over 3n over n plus 2 over n. So that is just going to be equals 2 over 3. So actually, the upper bound of the sequence that it doesn't quite reach but nearly does is 2/3, which is in the context of this particular sequence is quite a long way away. But either of those methods conclusively show that there is an upper bound to the sequence, and the lower bound is clearly the first term once you have shown that the sequence is monotone increasing.